Hi, I'm Mr. True. In this video, we're going to learn how to work with rational exponents. They're a natural extension of working with radicals, square roots, third roots, and fourth roots, and so on. These kind of questions with radicals, when you get into solving equations and getting more and more into the advanced mathematics, algebra, pre-calculus, calculus, they get a little bit cumbersome to work with. So we're going to learn how to use rational exponents, and if you don't move much further into mathematics, maybe you'll not see them very much beyond this. However, if you do continue on in your math studies, they become very, very handy as the algebra gets more complicated. So here's what we're going to have. We have b to the 1n power. That's going to be the first part of the video. We're going to have a rational or fractional exponent with a numerator of 1, and then in the next frame we'll move into having a variable both in the numerator and denominator of this fractional exponent. And again, we're learning this because it makes dealing with radicals much easier when you start getting into more advanced mathematics and solving equations as well that deal with radicals. For any real number b and any positive integer n, b to the 1n power is equal to the nth root of b. So you can see in a fractional exponent, a rational exponent, we're not sure what the numerator does yet, but the denominator is going to be simply the root. So if we're dealing with the square root, that'd be the b to the 1/2 power. If we're dealing with the third root, that would be b to the 1/3 power. Now, we have a bit of a problem though when b, the base, is less than 0. That means it's negative. And n is an even number because you can't take the square root of a negative number. You can't do the square root, say, of -4. It's not 2, nor is it -2. There is no answer unless you're learning about imaginary or complex numbers and solutions. So when b is less than 0, negative, and when n is even, which means you might have a complex root. That means that the root might be imaginary. So we're going to deal with a couple of examples, and it looks like they're all going to be numerical. We'll have some algebraic examples in the next part of the video. We have 81 to the 1/4 power. Now we're just learning how to deal with fractional exponents, so let's just make sure that we understand again that denominator is the root, so we can rewrite this as the 4th root of 81. And we're doing all these without the aid of a calculator, so the roots are going to have to be, especially when we start talking about 3rd, 4th, 5th root, and so on, we probably have some pretty basic or small numbers that have been raised to those high powers. So the 4th root of 81, what number multiplied by itself is going to equal 81? And it has to get multiplied by itself 4 times. Well, the smallest number that really changes as you multiply it by itself is going to be 2. I'm dealing with positive numbers here. So we have 2 times 2 is 4, times 2 again is 8, times 2 is 16. Okay, so 2 is too small because 2 to the 4th is equal to 16. So what about 3? 3 times 3 is 9, times another 3 is 27, times another 3 is 81. So this is equal to 3 because, again, as a check, 3 to the 4th power is equal to 81. When you do 3, 3, 3, and 3, multiply together, you do get 81. Okay, now you might remember that when you take even roots like square roots, the square root of 4, like I just mentioned a second ago, it wasn't 2 nor was it -2. If the textbook gives you the radical or the root here, we have a 1/4 power, so we're being asked for the 4th root. If the textbook puts that in there, they are only going to be expecting the positive root, unless, of course, they put a plus or a negative out front. So even though when you take an even root of a value, there is technically 2 possible answers, you want to follow the notation that's in the book. If you introduce your own even root, then you do need to include both the positive and the negative answer. So I'm going to say that this is simply 3 because we only had a nothing indicated out front whether we wanted a positive or negative answer. Okay. Over here, we have -16 to the 1/2 power. So now we know that this is a power of 1 and a root of 2. So we're looking for the second root or the square root of 16. Well, the square root of 16 is equal to 4. But we can't take a square root or 4th root or an even root of a negative number. So is that negative in the front of the 16 a problem? Well, let's not forget that exponents only act on the base in which they sit. So the only thing that has the power of 1/2 is the 16, not the negative sign that's out front. And we can rewrite this as negative 1 times 16 to the 1/2 power, which is equal to negative square root of 16, which is again negative 4. Now we see the negative is in front of our negative root, so we are looking for that negative answer, so negative 4 is what we are dealing with. However, here, now we have a problem because this is rewritten to get you back into that radical form that you might be comfortable with, equal to the square root of negative 16. And unless you've learned about complex or imaginary solutions, and you would say there's no solution to the square root of negative 16. If you have learned about imaginary or complex solutions, you would say it was equal to 4i. This might be getting ahead of you where you are in your math class, but just for argument's sake, because we're all using different books, I'm sure, watching these videos, we can rewrite this as the square root of negative 1 times the square root of 16. And that I that I just wrote there a second ago, that came from the square root of negative 1. The square root of negative 1 is I. The square root of 16 is 4. If you haven't learned about that and you're curious about it, just look up imaginary or complex solutions or roots. Okay, now here I have negative 125 again, another negative inside these parentheses. So the negative has a root applied to it, that's a root of 3. But we can take an odd root of a negative number. The cube root of negative 8 is negative 2, because negative 2 times negative 2 is positive 4, but then when you bring in that third negative 2, it goes back to negative 8 and you're okay. So you can take an odd root of both a positive and a negative number. If we look here, it said that for any positive integer n, so it's saying that our n is in the fraction or the denominator of our fractional exponent. So it's basically saying that our fractional or rational exponent needs to be positive, and here it's negative. So is that a problem? Is this negative 1/3 a problem based on this definition? Well, not really. We just need to rewrite it so that we don't have a negative exponent, and then we can apply this rule for doing b to the 1 over n power. If you have a negative exponent and you want to get rid of it, you take the base that has that negative exponent and move it. Whether it's in the numerator, like here, we're going to move it into the denominator, or if it was in the denominator, you move it up to the numerator. We have, therefore, 1 over negative 125. We're not getting rid of the negative that's in front of the base, but we are going to be able to take that negative 1/3 and write it now as positive 1/3. Now I'm not going to write this in radical notation because ultimately we are trying to get you used to and learning about fractional exponents. You again may not see really what their benefit is until you get into some higher level maths, or maybe at the end of this particular math class that you're in now. The cube root of negative 125 is, it ends in a 5 here, so it's probably going to be 5. So negative 5 times negative 5 is positive 25, and another negative 5 is your negative 125 that we were hoping for. So this is equal to negative 5. So our final answer is negative 1/5, or negative 1/5, or 1 over negative 5. All of those are equivalent solutions. Doesn't really matter where you put the negative sign, whether it's numerator, denominator, or right in the middle of that fraction. Okay, so what happens when the numerator is not just a basic 1? Now, b to the x over y power. For any real non-zero b and any integer x and y with y being greater than 1, b to the x over y power is equal to the y root of b to the x, or b to the y root, and then that entire expression or result being raised to the x power. So basically, in summary, your numerator of your fractional exponent, your rational exponent, is the power, and the denominator is the root. Once again, if your base is negative and you are taking an even root, you may have a complex or imaginary solution. So we have 64 to the 2/3 power. Again, doing this off the top of our head without the aid of a calculator. It is going to be easier for you to do the root before you do the power. It keeps the number smaller. So the third root of 64. 2 times 2 is 4, times 2 is 8. that's wrong. 3 times 3 is 9, times 3 is 27. Okay, that's no good. 4 times 4 is 16, and 16 times 4 again is 64. So the third root of 64 is equal to 4. We have not applied the power of 2 yet, so 4 squared is equal to 16. Over here, we have just a little bit of algebra. We've got, when you multiply like bases, you're supposed to add those exponents. So let's get that phone. Oh, the wifey got it. All right, never mind. When you multiply like bases, you want to add those exponents. So even though, this is really more about reminding you how to add fractions than really, so much dealing with the power over root process here, the fractional exponents. So we multiply those like bases. We want to add those exponents. Now, what common denominator do we have between 5 and 3? What is the lowest common multiple between 5 and 3? Well, that's going to be 15. 3, 6, 9, 12, 15. Oh, okay, 5 goes into 15. So we're going to multiply the numerator and denominator here by 3 to get that denominator to be 15. So 3 times 3 is equal to 9, so we have x to the 9 power over 5 times 3, which is 15. Times, now how are we going to get that 3 to have that fraction of 1/3 to have a denominator of 15? How do we turn that 3 into a 15? We got to multiply it by 5. So multiplying both the numerator and denominator by 5, we get x to the 5 over 15th power. And now we have those common denominators, so we can multiply those like bases and add the numerators, or excuse me, the exponents. So that base is going to get copied again, and we have 9 plus 5 over the common denominator of 15. So we have x to the 14 over 15. And that, there's nothing to simplify there, so we're just going to leave it that way. We have the fourth root of 32 over the square root of 2. Now, 32 is divisible by 2, but don't be tempted to do that and say that it's equal to 16, because these radicals do not have the same root. A square root and a fourth root, those don't they don't go together at all, basically. We're going to force them to go together by going from radical format into fractional or rational exponent form, and just see if we can make some nice stuff happen here. Okay, so this is going to be 32 to the 1/4 power. And here we have 2 to the 1/2. So now we're dividing, but we're still not going to get those bases to go together. Like, it'd be nice if we could say, when we divide like bases, we can subtract the exponents. So could we play around with 32 to be able to rewrite it so it does have a base of 2? How well do you know your powers in your multiplication? 2 to the 5th is equal to 32. So actually we can get the numerator to be written so it has the same base as the denominator, and that will allow us to simplify the fraction. So 32 is 2 to the 5th raised to the 1/4 power. We didn't apply that fourth root, over 2 to the 1/2 power. When you have stacked exponents, when you have one base, that base of 2, and you have stacked exponents, they're kind of touching or just separated by that parentheses right there, then you need to apply the power rule for exponents. And when you do that, you multiply them. So 5 times 1/4, 5 times 1/4. Let's not forget that when we multiply fractions, we don't need common denominators, just go across the top. So it becomes 5 times 1 is 5. And then 1 times 4 is 4, so it's 2 to the 5/4 power over 2 to the 1/2 power. Okay, so we're going to now divide those like bases and subtract the exponents. So this becomes 2 to the 5/4 minus 1/2. We need a common denominator, so we can make a 2 into a 4 pretty easy. Just multiply it by 2. So we're going to multiply the numerator and denominator by 2. So 1 times 2 is 2, and 2 times 2 is equal to 4. So this becomes 2/4, and then 5/4 minus 2/4 is 3/4. So we end up with 2 to the 3/4 power. And since my original problem was in a radical format, we can now take that rational or fractional exponent form and put it into radical form to match the the original problem. So this is going to be 2 to the third power, or the fourth root of 2 to the third power. Yeah, and that's done. Okay, now my last problem here is basically going to be just for reminding you how to rationalize denominators. So we have x to the 1/2 power. Well, that's x to the 1/2 second root. So we have the square root of x minus 5 over 2 times x to the 1/2, and that's going to be 2 times the square root of x plus 3. Now, hopefully you remember how to rationalize a denominator that has a radical in it. When it's a binomial, you want to multiply by the conjugate. That means you just want to change the middle sign of the binomial. I don't really want to work with radicals though, because I'm assuming you're already comfortable with that. And we're trying to learn a new notation. So we're going to leave it in fractional exponent form, and we're going to multiply the numerator and denominator by the conjugate of the denominator, trying to get rid of that power of 1/2, because it is a square root in the denominator, and we want to get rid of that. So we're going to multiply the numerator and denominator by 2x to the 1/2 power minus 3. And hopefully we get that fractional exponent to go away in the denominator. So we have x to the 1/2 times, let's see here, pick a number of colors, you can see what I'm going to do here. Okay, so we have x to the 1/2 times 2x to the 1/2, so we're going to just simply, 1 times 2 is equal to 2. And x to the 1/2 times x to the 1/2. When you multiply like bases, you're supposed to add the exponents. I mean, if this were just 1x times 2x, you would say 2x squared without hesitating. Well, that square comes from adding the exponents of 1. So 1/2 plus 1/2 is just 1. So we're going to have 2x to the first power, because 1/2 plus 1/2 is 1. And then x to the 1/2 power times negative 3 is minus 3x to the 1/2 power. And then going to the next term, negative 5 times 2 is negative 10x to the 1/2 power. And negative 5 times negative 3 is positive 15. All over 2x to the 1/2 times 2x to the 1/2. 2 times 2 is equal to 4. And again, we're going to add those exponents when we multiply like bases, and 1/2 plus 1/2 is equal to 1, so it's just going to be 4x. 2x to the 1/2 times negative 3 is negative 6. X to the 1/2 power. And then we have positive 3 and positive 2, so we're going to get positive 6. X to the 1/2. See how these are going to cancel out? That's why we want to multiply by the conjugate. This is a difference of squares pattern, by the way. If you've just learned factoring, a plus b times a minus b is a squared minus b squared. There's no middle term. And I'm just doing this for teaching. It's kind of academic. I know that those middle terms are going to cancel out anyway. Positive 3 times negative 3 is negative 9. And let's clean this up a little bit. We have 2x. We have negative 3 and negative 10, which is negative 13x to the 1/2 power, and positive 15 over 4x minus 9. Because these middle terms are going to cancel out. Now, this is a difference of squares here. It's kind of hidden because the x has an exponent of 1, but remember it originally started off with an exponent of 1/2. And when you square root x, you get x to the 1/2. 4 is a perfect square, 9 is a perfect square, so this is a difference of perfect squares, that pattern that we got from multiplying a plus b times a minus b. How many examples do I have left? We got 3 more examples, so I'll be right back. Woo! Okay. This first example of what is remaining, we have x to the negative 4/7 power. Okay, we're going to write that so we don't have the negative exponent, which means we're going to have 1 over x to the 4/7. Well, I just did a problem where we had to rationalize the denominator because we had a fractional exponent in the denominator. That is having a radical sign in the denominator. We don't like that. So we have that problem here. Now, What am I going to multiply the numerator and denominator by to make this fractional exponent go away? Well, the only way I'm going to change that exponent is if I multiply by a base of x, because when you multiply like bases, you add the exponents. So what am I going to multiply? I'm going to multiply by x to the some power that is going to be able to add to 4/7 and not have a fraction. You know, I want the fraction to go away. So I want this to equal the smallest value that is basically a whole number. So what am I going to add by 4/7 to get 1? Well, if I add it by 3/7, 4/7 plus 3/7, 4 plus 3 is 7/7, which is 1. So if I multiply by x to the 3/7 power in the numerator and denominator, I'm going to have the bottom exponents add up to 1 and thus get rid of my fractional exponent, get rid of my radical sign. So I have x to the 3/7 power over x to the 7/7 power, which of course we know is equal to 1. So that's our final answer, x to the 3/7 over x. Okay, when we have nested radicals together, that can confuse people. I remember even finding it confusing for myself when I was in school. And this problem you can work out without going through this process I'm about to do, but of course I want to give you a somewhat easy example so that when you get to some problems similar to this that are all maybe algebraically, that you can't just think your way through the problem, you'll see that, yes indeed it does work. I'm going to show you how to write this with fractional exponents, and well, let's just see what we have. We have 729 raised to the power of 1 and the second root. So this is going to be equal to 729 to the 1/2 power. Now that is being raised, or being not raised, but cube rooted again. So if I take this outside cube root and write it as a fractional exponent, then it's going to look like this, with another set of parentheses come in, and we have another power of 1/3, not 1/2. Okay, so you see what's happening here? We have a like base with two stacked exponents. When you multiply, or when you have those stacked exponents, you need to multiply those together, do that power rule for exponents. So we have 729 raised to the 1/6 power, because 1/2 times 1/3 is 1/6. 1 times 1 is 1, 2 times 3 is 6. So now all we have to do is the 6th root of 729, and I guess kind of annoyingly I picked a somewhat large number here and a large, whoops, let me get my head on straight here. That is the 1/6 power, so that is the 6th root. Now I highly doubt that many of us have 6th roots in our head, but I'm doing this out of 8 of a calculator, so it can't be too big of a number. 2, 4, 8, 16, 32, 64. It's not 2 to the 6th. 3, 9, 27, 81. 81 times 3. 80 times 3 is 240, and 240 times, with an additional 3 added in, because it was 81, not 80, is 243, and 243 times 3 again is 729. So the cube root, or excuse me, the 6th root of, that's stuck in my head for some reason, the 6th root of 729 is equal to 3. Okay, here we have the 6th root of 49 times x to the 12th power times y to the 4th. Now, we talked about simplifying radicals, so there is another way of doing this problem, but again, working with it in the format of having fractional exponents or rational exponents, we can write this as, let's see here, 49 is 7 squared, so 7 squared, we have x to the 12th power, we have y to the 4th, and all of that is getting raised by the 1/6 power, because we have the 6th root of all of that. So what do we have here? Well, I've got a base inside of yet another power, so we're again going to apply the power rule and bring that 1/6 through here, kind of like we're distributing it, even though it's not technically what we're doing. But we have 7 to the 2/6 power. That's going to reduce to 1/3 in a second. We have x to the 12/6 power. and y to the 4 over 6 power. So 2 6 reduces to 1/3, so we have 7 to the 1/3. We have 12 divided by 6 is equal to 2, so we have x squared. And then finally we have y to the 4 6. 4 over 6 reduces to 2/3. Okay, so we can write that as our final answer, or if we want to go back into radical form, because that is the format of our original problem, we have a third root of 7 and a third root of y. So both the 7 and the y have that same value, that same root applied to them, so we can put these very, very easily into one radical and say that this is equal to x squared. What do we have? 7 to the first and y squared. So 7y squared, the third root, because of that denominator of 3, of the third root of 7y squared. That is the end of my example. So, I'm Mr. True. Bang! Go do your homework.